Hello, calculus. Volumes of solids of revolution. This is our Monday or later viewing, so that's a third. So we're going to branch off of what we do know. We've been looking at 2D area for quite a while now. Ever since we entered integral land, we've had the discussions on finding areas, and specifically areas under a curve. So let me just review that what the integral did for us. It took a box. We'll do an upper box here. And we took the area of this rectangular box, and we are going to add these boxes up, an infinite number of them, and this little almost S symbol is adding all the areas of the boxes from A to B, and there are an infinite number of them, and each of their width is dx, which is infinitesimally small, and the height is the function, so f of x. So the height is related to the name of this curve, and we'll call it f of x. So we've been using the integral to get the area under a curve for some time now. So just recall how that works. And also, before I go on, I want to recall from geometry, if you had a circular cylinder, and like this. So the cylinder is got a circular base, and this is the, I guess I'll call it the thickness, we could call it the height or the depth, the thickness of the cylinder. So let me remind you, the volume of a cylinder is going to be the area of the base, which in this case, since it's a circular cylinder, it's pi r squared, and we're going to multiply it times the thickness. So I'll just call it T for thickness. Alright, so let me remind you of those concepts. We're going to put those together in a new way and look at volumes of revolution. Volumes of solids of revolution. So we're going to be revolving something in order to make a solid and find its volume. I find it one of the best calculus lessons because, I don't know, it just is amazing to me what a little bit of calculus can do so much. Alright, so I'm going to teach theory, and then we'll do one example. And it looks like this. Suppose we have a curve that comes like this. We'll call it f of x. Alright, so f of x is our curve. And we are going to look at this curve. We're interested in it from A to B. Alright, so I promised you something was going to revolve. So I'm going to revolve this curve around an axis. So I'm going to revolve it around the x-axis. So I'm going to take it, and my drawing skills are going to be lacking, but it's going to come out from the plane, this 2D plane. We're going to the 3D plane. Is becoming a volume. So this area bounded by this curve, that whole area, is going to come out and revolve around the x-axis and come back. So when it does that, can you envision the actual shape that is created? I will try to draw it. So we're going to revolve it. So this will come down here, and all of this will be rounded. So I have revolved that, and this will be rounded. So it kind of looks like a sideways Hershey's Kiss without the tip on it. I don't know. So imagine like a Hershey's Kiss. The bottom looks like that, and we're going to cut the top off and put it sideways. I don't know. You can envision it as something else, maybe a light bulb that comes out of a, you know, the kind that you put up into a recessed lighting fixture. I don't know. But anyway, in industry, there's lots of shapes that have to be made, and we have to know the volume so we know how much material. This is solid, so we have this volume of a solid from a revolution of a area under a curve. Alright, so let me get rid of these little lines so you can see what I'm going to do next in a more clear way. Alright, so now I'm going to take a slice from this. It can be down here, in the middle. I'll take a slice right here. I don't care. So, alright, this slice of this volume, solid, this solid, I'm going to take a slice of it. So, I'm going to cut right through it, and I'm going to pull out a slice. So when I pull out that slice and lay it in front of you, can you envision that the slice has a thickness? So here's the thickness of my slice. It's also right here. And it is a complete circle. Here it kind of looks oval-like, but it's just perspective. When I pull the slice out and lay it out, it is a complete circle. So what's the volume? This slice is really a circular cylinder that is very thin. So the area is pi r squared of the base, and I'm going to add the thickness of the, which I call T. So the volume of just that is sort of like a penny, a large penny. So the volume is pi r squared times the thickness. So in our story over here, where we have the slice out of this, we have pi r squared, and the thickness is, let me use my two thumbs. The thickness is between my two thumbs. And of course, as I want to do in calculus, I'm going to make that thickness infinitesimally small. And I am interested in pi r. When it says r, where is r? Where's the radius of this one particular slice that I pulled out? Well, the radius is linked to that point on the curve, and it's above the x-axis somewhere. I'll call the value x, so I'll call this point x comma y. So if I do that, the radius is from here to here. Since it's right on the function, can you see it is the function evaluated at that value for x? And what if I do that a million, billion, infinite number of times? Then I add up all the volumes, and I have the volume of this whole solid. And I'm going to add them all up, the infinite number with the integral. And the slices are going to start at A, and there's going to be an infinite number of them. They're all circular cylinders, and they're going to add up from A to B, and they're going to be pi r squared. And when I get to the thickness, I'm going to call it dx, because the distance between my thumbs is infinitesimally small, and it's on the x-axis, it's a change in x. So I have dx. The radius I can improve on, and that means the radius, which I dotted from here to here, I'll make it more obvious here. From here to here is the radius of that one disk. And I can call it y, because it is the distance on the function called y. If we call this x over and y up, the radius is y. So I'm going to, instead of calling it r, I'm going to call it y. And instead of pi on that side of the integral, it's a constant, so it can come across the integral sign. So another way I can represent y is f of x. So either way is good. So we're going to go, I'll go with that version. So this is the theory. Now let me show you a particular case. Alright, before I do that, let me go the other way. So I think I can fit it on here so you can see. What if I revolve it around the y-axis? Let's take another function. Let's take y equals f of x. I wouldn't call it y equals f of x this time, because I'm doing this in terms of y. I'm going to call it x equals f of y. And now this, I'm going to take this f of y. Sorry, I'm so used to saying f of x. And I'm going to revolve it around the y-axis this time. So what kind of solid will be formed if I take this area, say right here, and revolve it around the y-axis? So can you see it creates a solid bowl, or maybe a bullet, some sort of object as pictured here. Right. Well, let me remove this again. So I'm going to take a slice this time, and the slice is like a penny. It is still circular. So when I pull it out, it's going to be circular, and the radius this time is going to be still on the function, but it's going to go this way. So what will change when I do the theory? I'm still going to have pi from, I'll call this c to d, the integral from c to d. So all of the slices are going to be at different spots, an infinite number adding up from c to d to add up to the volume of the entire solid. So I'm going to take just one of them here and build the formula. So it's going to be pi, and there's my pi. R this time is from here to here, so that's a value. If we call this x over and y up, as we normally do, the radius is this time is the value for x. So we're going to put f of y, or x. So we're going to call that is the, you can tell it's x by looking at its length. And where would you read it? You would read the length on the x-axis. Here the radius was read on the length of it was read on the y-axis. So I'm just going to call it x, and I may also call it f of y. So I have my choice, but that radius is squared. And what about the thickness of this penny or this slice? This time I put my thumbs in this direction, and the distance between them is the thickness. It is a change in y this time, so I'm going to call it dy. Alright, normally we like the variable to match the differential. The variable of the integration is indicated here. So I'm going to call this f of y, but it is equivalent to x, so that's fine as well. Alright, so that's the theory. Alright, let's see how we can put it into practice. Very, very powerful stuff. Alright, so I'm going to do one of them. I think I will do one. Yeah, I think one or two. So let's see how far I get. The function is y equals the square root of sine of x. So I'm going to take the area bounded between that curve, the x-axis, and 0 pi. I'm going to take that area and revolve it around the x-axis. Alright, so let's take a look at it. So the graph between 0 and pi of the square root of pi looks something like that. It's just sort of a hill, like that. So when we have that, we're going to take that area right in here and revolve it around the x-axis. So when that goes all the way around in 3D motion, it creates a 3D figure like that. Maybe a lemon, something like a lemon. Can you visualize it as a 3D figure? It's hard to draw it. So I'm going to take a slice out of it. I do like to draw my slices. And there is the volume of 1. Of course, I'm going to do that an infinite number of times with the integral. These slices are going to add up across the lemon from 0 to pi, pi r squared, and this thickness is dx. You can always tell, pretend it's a penny, and the thickness is right there, and that's a change in x. So infinitesimally small changes in x are written as dx. Now I just need to improve on the radius. The radius is related to that point. We went over x and up y. So which of those variables will indicate this length? It is a y variable, so I can call it y squared. But we know that in this case y is equal to the square root of sine of x. And I want to work in x. So I'm going to do the square root of sine of x squared. Square roots are welcome in these problems because when you square them, like you have to for circular base areas, they disappear. So when I take that integral, and you can verify this and on your calculator or just by hand, it's rather a quick integral to take. It comes out to be 2 pi. Alright, so that is the volume. So that is units cubed. Whatever unit I'm working in, it's now a cubic unit. Alright, so verify that I got that correct. Alright, then I'll put in, as in anything that we've learned, there's always complications. So let me give you one complication, and that'll be it for one of these lessons. It's 4 different aspects. So I'll probably do 2 in one video and then 2 in the other. So it's a 2-part topic. Alright, so let's look at the area. Let's see, we have the function is 2 minus x squared. So I want the area bounded by this function and this function. We always start with an area, and then we're going to revolve it somewhere. But instead of around the x or the y-axis, I can also revolve it around any line that's vertical or horizontal. So I'm going to go around the line y equals 1. So let me show you what that might look like. So the sketch, always start with the sketch. The area bounded between these 2 curves, excuse me, this is the frowner turned up, smiler turned upside down, so it's a frowner raised up 2. So like that. And the line y equals 1, or g of x is like y equals 1, is like this. So let me get rid of these extra lines. We want the area between, that's bounded between those 2 curves. So, alright, so we're going to take that and we're going to revolve it around that line, y equals 1. So it's going to come out along that line and go back in the board into the, in a 3D manner. So it looks like we have another lemon. So with that, let's go ahead then and discuss the integral. This integral, I'm going to remove some of these lines so I can draw my representative slice. We call these slice disks. So volume of revolution disks. Alright, so let me draw my pennies or my disc. I'm going to take one slice like this and I'm going to add them up from what to what? Well, I need to know the intersection point, just the x value of it. x1 to x2. So I've set these two functions equal, and when you do that, it turns out that we get 1 and negative 1. And you can verify that. And when we have pi, what's the radius of this disk that I've drawn? I hope it shows up. I have some extra things going on here. Alright, so the radius of 1 is right there. Is that an x or is that a y? It's associated with the point, always a point on the curve. So that point is x over and y up. So it's going to be associated with the y. But remember, y is going to go from the x-axis. So there's a little adjustment. As I said, it's a complication. So if I said y, remember here's the x-axis. This is the line y equals 1. But the radius of this disk goes from here to here. So that's why I always say draw it. Because this x value means from the origin I went over x and up y. This whole thing is y, and I only want a portion of that. How can I get from the y value to the real radius of the disk? And that is because this value I know, from there to there, is 1. So, because that's the line y equals 1. You see then the radius that I need is going to be the x value minus the 1. So, I'm sorry, did I say x? It's going to be the y value minus the 1. Y minus 1, that's the radius, and it's squared. And the thickness of my penny is the difference between my thumbs is a change in x, so it's dx. So I prefer to write this all in terms of x, but I know y equals 2 minus x squared. So I can do 2 minus x squared and the minus 1. And that will simplify. The 2 and the minus 1 become a 1 minus x squared. Then you square it, take the integral, multiply it by pi. So when you do the integral, you put in the upper minus the lower limit of integration. All that comes out to be 16 pi over 15. Alright, and again that's some units cubed. Alright, so that's how you do the basic ones and how you do one with a complication. Alright, so that will set you up for success on the next time that we meet. And we will be practicing volumes of solids of revolutions using the disk method. Alright, carry on class, carry on.